Hello friends, in the preceding chapters we made extensive use of the property tables. We tend to take the property tables for granted, but thermodynamic laws and principles are of little use to engineers without them. In this and the next few lectures, we shall be focusing our attention on how the property tables are prepared and how some unknown properties can be determined from limited available data. It will come as no surprise that some properties such as temperature, pressure, volume and mass can be measured directly. Other properties such as density and specific volume can be determined from these using some simple relations. However, properties such as internal energy, enthalpy and entropy are not so easy to determine because they cannot be measured directly or related to easily measurable properties through some simple relations. Therefore, it is essential that we develop some fundamental relations between commonly encountered thermodynamic properties and express the properties that cannot be measured directly in terms of easily measurable properties. To do so, we need to study a bit of calculus, partial derivatives and associated relations. By the nature of the material, this discussion would make extensive use of partial derivatives. Therefore, we start by reviewing them. Many of the expressions developed in this lecture are based on the state postulate, which expresses that the state of a simple compressible substance is completely specified by any two independent intensive properties. All other properties at that state can be expressed in terms of those two properties. Mathematically speaking, Z is equal to Zxy. Here x and y are the two independent properties that fix the state and Z represents any other property. Most basic thermodynamic relations involve differentials. Therefore, we start by reviewing the derivatives and various relations among derivatives to the extent necessary in thermodynamics. Consider a function f that depends on a single variable x, that is, f is equal to fx. This figure here shows that a function that starts out flat but gets rather steep as x increases. The steepness of the curve is a measure of the degree of dependence of f on x. In our case, the function f depends on x more strongly at larger x values. The steepness of a curve at a point is measured by the slope of a line tangent to the curve at that point, and it is equivalent to the derivative of the function at that point defined as df upon dx is equal to limit as delta x approaches 0 of delta f divided by delta x and is equal to limit as delta x approaches 0 of f x plus delta x minus fx divided by delta x. Therefore, the derivative of a function fx with respect to x represents the rate of change of f with x. Now consider other intensive properties that can be determined as a function of the two independent properties, that is, P is equal to PTV, U is equal to UTV and H is equal to HTV and so on. These are all functions of two independent variables of the form z is equal to zxy, with x and y being the independent variables. It might also be recalled that the differential of every property is exact. The differentials of non-properties such as work and heat are inexact. functions of two independent variables. Let us now review briefly some concepts from calculus about functions of two independent variables and their differentials. The exact differential of a function z continuous in the variable x and y is dz is equal to partial derivative of z with respect to x into dx keeping y constant plus partial derivative of z with respect to y into dy keeping x constant. This can be expressed alternatively as dz is equal to m dx plus n dy. Here the coefficient m is the partial derivative of z with respect to x, the variable y being held constant. Similarly, n is the partial derivative of z with respect to y, the variable x being held constant. If the coefficients m and n have continuous first partial derivatives, the order in which a second partial derivative of the function z is taken is immaterial. That is, partial derivative of m with respect to y with x as constant is equal to partial derivative of n with respect to x keeping y constant. This is an important relation for partial derivatives, and it is used in calculus to test whether a differential dz is exact or inexact. In thermodynamics, this relation forms the basis for the development of the Maxwell relations discussed in the next section. In other words, we can say that this equation here indicates that the mixed second partial derivatives of the function z are equal. The relationship in equation is both a necessary and sufficient condition for the exactness of a differential expression, and it may therefore be used as a test for exactness. When an expression such as m dx plus n dy does not meet this test, no function z exists whose differential is equal to this expression. In thermodynamics, this equation is not generally used to test exactness, but rather to develop additional property relations. Reciprocity and cyclic relations. Next, we develop another two important relations for partial derivatives, the reciprocity and the cyclic relations. The function z is equal to zxy can also be expressed as x is equal to xyz if y and z are taken to be the independent variables. Then using equation A, the total differential of x becomes dx is equal to partial derivative of x with respect to y keeping z constant into dy plus partial derivative of x with respect to z keeping y constant into dz. Eliminating dx by combining the above two equations, we have dz is equal to partial derivative of z with respect to x keeping y constant into partial derivative of x with respect to y keeping z constant plus partial derivative of z with respect to y keeping x constant into dy plus partial derivative of x with respect to z keeping y constant into partial derivative of z with respect to x keeping y constant into dz. Rearranging, we get this equation: partial derivative of z with respect to x keeping y constant into partial derivative of x with respect to y keeping z constant plus partial derivative of z with respect to y keeping x constant into dy and is equal to 1 minus partial derivative of x with respect to z keeping y constant into partial derivative of z with respect to x keeping y constant into dz. The variables y and z are independent of each other and thus can be varied independently. For example, y can be held constant, that is, dy is equal to 0, and z can be varied over a range of values, that is, dz not equal to 0. Therefore, for this equation to be valid at all times, the terms in the brackets must be equal to 0 regardless of the value of y and z. Setting the terms in each bracket equal to 0 gives partial derivative of x with respect to z keeping y constant into partial derivative of z with respect to x keeping y constant is equal to 1, which gives partial derivative of x with respect to z keeping y constant is equal to 1 upon partial derivative of z with respect to x keeping y constant, and partial derivative of z with respect to x keeping y constant into partial derivative of x with respect to y keeping z constant is equal to minus partial derivative of x with respect to y keeping x constant, which gives partial derivative of x with respect to y with z constant into partial derivative of y with respect to z with x constant into partial derivative of z with respect to x keeping y constant and is equal to minus 1. The first relation is called the reciprocity relation, and it shows that the inverse of a partial derivative is equal to its reciprocal. The second relation is called the cyclic relation, and it is frequently used in thermodynamics. I can understand that calculus is a little tough nut to break, but practice makes a man perfect. Partial derivatives are powerful tools that are supposed to make life easier, not harder. The Maxwell relations. The equations that relate the partial derivatives of properties P, V, T and S of a simple compressible system to each other are called the Maxwell relations. They are obtained from the four Gibbs equations by exploiting the exactness of the differentials of thermodynamic properties. Two of the Gibbs relations were derived in earlier lecture and were expressed as du is equal to TdS minus PdV and dH is equal to TdS plus VdP. The other two Gibbs relations are based on two new combination properties, the Helmholtz function A and the Gibbs function G, defined as A is equal to U minus Ts and G is equal to H minus Ts. The Helmholtz and Gibbs functions are properties because each is defined in terms of properties. From inspection of these two equations, we find that the units of A and G are same as those of U and H. These two new properties are introduced solely because they contribute to the present discussion and no physical significance need to be attached to them at this point. Forming the differential dA, we get dA is equal to du minus dTs and is equal to du minus TdS minus S dt. Substituting the value of du minus TdS is equal to minus PdV from Gibbs equation, we get dA is equal to minus PdV minus S dt. Similarly, forming the differential dG, we get dG is equal to dH minus dTs and is equal to dH minus TdS minus S dt. Substituting the value of dH minus TdS is equal to VdP from Gibbs equation, we get dG is equal to VdP minus S dt. Property relations from exact differentials. The four differential equations introduced in the previous section provide the basis for several important property relations. Since only properties are involved, each is an exact differential exhibiting the general form dz is equal to m dx and is equal to n dy. Underlying these exact differentials are respectively functions of the form u s v, h s p, a y t and g t p. Let us consider these functions in the order given. The differential of the function u s v is du is equal to partial derivative of u with respect to s keeping v constant into ds plus partial derivative of u with respect to v keeping s constant into dv. By comparing with Gibbs' first equation, we conclude that t is equal to partial derivative of u with respect to s keeping v constant and minus p is equal to partial derivative of u with respect to v keeping s constant. The differential of the function h s p is dh is equal to partial derivative of h with respect to s keeping p constant into ds plus partial derivative of h with respect to p keeping s constant into dp. By comparing with Gibbs' second equation, we conclude that t is equal to partial derivative of h with respect to s keeping p constant and v is equal to partial derivative of h with respect to p keeping s constant. Similarly, the coefficients minus p and minus s of this equation are partial derivatives of a v t. Therefore, minus p is equal to partial derivative of a with respect to v keeping t constant and minus s is equal to partial derivative of a with respect to t keeping v constant. And the coefficients v and minus s of this equation are partial derivatives of g t p. Therefore, v is equal to partial derivative of g with respect to p keeping t constant and minus s is equal to partial derivative of g with respect to t keeping p constant. As each of the four differentials introduced here is exact, the second mixed partial derivatives are equal. Thus, comparing these two equations, we find that t plays the role of m in B1 and minus p plays the role of n in B1. So, partial derivative of t with respect to v keeping s constant is equal to partial derivative of p with respect to s keeping v constant. In equation A2, t and v play the roles of m and n in equation B1 respectively. Thus, partial derivative of t with respect to p keeping s constant is equal to partial derivative of v with respect to s keeping p constant. Similarly, from these two equations follows that partial derivative of t with respect to p keeping s constant is equal to partial derivative of v with respect to s keeping p constant and partial derivative of v with respect to t keeping s constant is equal to minus partial derivative of s with respect to p keeping t constant. These four equations are known as the Maxwell relations. They are extremely valuable in thermodynamics because they provide a means of determining the change in entropy, which cannot be measured directly by simply measuring the changes in properties P, V and T. Note that the Maxwell relations given here are limited to simple compressible systems. However, other similar relations can be written just as easily for simple compressible systems such as those involving electrical, magnetic and other effects. Conclusion: some thermodynamic properties can be measured directly, but many others cannot. Therefore, it is necessary to develop some relations between these two groups so that the properties that cannot be measured directly can be evaluated. The derivations are based on the fact that properties are point functions and the state of a simple compressible system is completely specified by any two independent intensive properties. The equations that relate the partial derivatives of properties P, V, T and S of a simple compressible substance to each other are called the Maxwell relations. So friends, that is it for today. See you in the next lecture with more on thermodynamics. Thank you very much.